So, our problem for today is problem 5.5 of the book Process System Analysis and Control, 3rd edition by Coughanowr. So, we are given a CSTR or a continuously steered tank reactor with an reaction of A to B, which is the reactant A to product B, and proceed at a rate of R equals to Kc naught. And it is assumed that constant density, constant volume, and also the flow rate, the inlet and the outlet flow rate is also constant. So constant feed rate. So we are tasked to find the transfer function relating the concentration of the outlet and the concentration of the inlet reactor. And secondly, we must catch the response of the reactor to a unit step change in CI. So in order to find the transfer function that relate the concentration of the outlet to the concentration of the inlet, we must first define an ODE that greatly define the system or the CSTR. So you can define the ODE using the mass balance around the reactor, which is in minus out plus generation equals to accumulation, whereas the in is equal to the flow rate multiplied by the inlet concentration minus the flow rate multiplied by the outlet concentration plus the generation, in which is the rate of disappearance of A times volume equals to the volume of the mixture times delta C naught over delta T. We can further simplify or rearrange this equation with these following steps. So FCI minus FC naught minus K C naught V equals to V DC naught DT. Combine like terms minus F plus KV C naught equals to V DCO DT. F over VCI minus F plus F over V plus K C naught equals to DCO DT. So we have already our ODE. Before we solve this equation by means of Laplace transform, we must introduce a deviation variable, in which deviation variable, right here, deviation variable CI equals to CI minus CI at steady state, and C naught equals to C naught and C naught as at steady state. So if this equation is at steady state, we can write this in the form of F over V CIS, define the steady state, F plus over V plus K C naught S equals to 0. And subtracting this equation from this equation, we can get F over V CI minus CIS minus F over V plus K C naught minus C naught S equals to DC naught minus DC naught S, or at steady state, DT. Substituting the deviation variable that we have introduced a while ago, F over V CI, or should I say yan, F over V plus K times C naught equals to DC naught DT. So we have already an ODE that consider the deviation variable that we have introduced. So we can already Laplace transform this equation to solve the transfer function. So the Laplace transform of this equation will be Ci minus F over V plus K C naught equals to dc naught over dt. Laplace transform is equal to f over v ci minus f over v plus k c naught s equals to s c naught s. Combining like terms, we can get this equation: c naught s times s plus f over v plus k equals to f over v ci naught, or should I say, sorry, cis. Now we can already find our transfer function by dividing both sides of the equation with cis, cancelling out this, and c naught s is equal to cis equals to f over v times 1 over s plus f over v plus k. This is already our transfer function, since the transfer function is equal to the output over input, right? So we can show this transfer function into the common form of the first order function. So we must show it as 1 over tau s plus 1. So how can we form this equation into the form of 1 over tau s plus 1? So here is the steps to get it. So we must show this transfer function into its common form, which is the 1 over tau s plus 1. We must distribute this v inside the parentheses. So c naught s over cis is equal to f over vs plus f plus kv. Dividing the numerator and the denominator with f plus kv will result to f over f plus kv over v over f plus kv s plus 1. Setting v over f plus kv equals to tau, which is our time constant. So to prove that it is our time constant, we must solve the units. Volume over time, cancelling out the volume, then it's time. Therefore, it is our time constant. So we can show the transfer function as c naught s cis equals to f plus kv over tau s plus 1, in which mo na niya tong transfer function na in the common form, the common first order form. But we can further simplify it by letting a is equal to f over f plus kv, since this form here is constant. All other parameters in the system is constant aside from the inlet and outlet concentration. So we can present the transfer function as c naught s over cis equals to a over tau s plus 1, right? So here is our simplified transfer function. So in order to sketch the response or the outlet concentration to your input or the inlet concentration, we must first get your c naught t by Laplace inversing the transfer function that we have derived a while ago. So here is our transfer function, and our input is a unit step input. So cis is equal to 1 over s. So this equation will become c naught s is equal to 1 over s times a over tau s plus 1. Unfortunately, we cannot derive this, or should I say, we cannot easily inverse the Laplace of this function here. So we must apply the technique of partial fraction to transform it into another form that can be easily Laplace inverse. So by applying partial fraction on this part of equation, it will become as a over s minus tau a over tau s plus 1 c naught s. So applying Laplace inverse, we can get c naught t is equals to a minus tau a over tau multiplied by e raised to the negative t over tau. Simplifying this, c naught t will be a times 1 minus e to the negative t over tau. Thus, having this equation, you can already sketch our graph or the response of the outlet concentration to your input, which is a step function, CIS.
So here's the graph of the response C naught to the step input Ci. As you can see, the response approaches the step input Ci. And when t approaches infinity, C naught t approaches A. Therefore, A is equal to your Ci. And this A is equal to F plus kV. So I hope you have learned something from me. Goodbye.